can see, it's important to be familiar with the phase relationships in RLC circuits as it was for RC and RL circuits. The second type of relationship is also important to remember when working with RLC circuits, Ohm's frequency relationships.
From your previous studies, you've seen that resistive components have no relationship to frequency, whereas reactive components do. There is an inverse relationship between capacitive reactance and frequency. And there is a direct relationship between inductive reactance and frequency.
These two fundamental types of relationships will serve as important guides in your analysis of RLC circuits. Because RLC principles are based upon what you've already learned, you know that both resistive and reactive values, which are measured in ohms, can be interchanged into Ohm's law. Now let's consider the combination of resistive and reactive opposition in RLC circuits by seeing how total impedance can be calculated.
As you know, impedance, designated with a capital Z, is measured in ohms. You've also seen that because it's an ohms value, impedance follows Ohm's law, where Z equals V divided by I.
But suppose that you don't know the total current. Let's derive a formula for total impedance in an RLC circuit based on the Pythagorean theorem.
Start with the formula for the total voltage in a series RLC circuit. V sub T equals the square root of V sub R squared plus the square of the quantity V sub L minus V sub C.
In algebra, you can divide each term of an equation by the same quantity without changing the equality.
Because current is the same throughout a series RLC circuit, divide each term in the equation by I sub T. At this point in the derivation, let's simplify the right side of the equal sign by squaring both sides of the equation. This will eliminate the radical sign. The right side of the equation now reads V sub R squared plus the quantity V sub L minus V sub C squared divided by I sub T squared. Because there is a common denominator on the right side, rewrite it as V sub R squared divided by I sub T squared plus V sub L minus V sub C divided by I sub T quantity squared. Now add parentheses on the right indicating that each quantity is squared. Since the current is the same throughout a series circuit, the I sub T's on the right can be freely replaced with I sub R, I sub L, and I sub C respectively. If you look inside each pair of parentheses, you'll find some Ohm's law relationships that have already been presented. For example, on the left of the equal sign, V sub T divided by I sub T is Ohm's law for impedance. V sub R divided by I sub R is Ohm's law for resistance. V sub L divided by I sub L is Ohm's law for inductive reactance. And V sub C divided by I sub C is Ohm's law for capacitive reactance. Since you're not looking for impedance squared, but the value of impedance, take the square root of both sides of the equation. This will yield the formula for impedance in a series RLC circuit. Z equals the square root of the quantity R squared plus X sub L minus X sub C quantity squared. You can see how this is still based on the Pythagorean theorem.
Let's analyze this series RLC circuit as an example. Assuming a resistance of 3 kiloohms, an inductive reactance of 9 kiloohms, and a capacitive reactance of 5 kiloohms, let's solve for the total circuit impedance. Substituting the example values into the formula for RLC impedance gives Z equals the square root of 3 kiloohms squared plus the square of the quantity 9 kiloohms minus 5 kiloohms. After completing the calculations, you find a total impedance of 5 kiloohms.
If the example circuit has an applied voltage of 10 volts, use Ohm's law to find the total current for this RLC circuit. I sub T equals V sub T divided by Z. Substituting the example values gives I sub T equals 10 volts divided by 5 kiloohms, which equals a total current of 2 milliamps.
In the same example circuit, since you now know the total current as well as the values of the resistor and the reactance of the capacitor and inductor, the voltage across each separate component can also be calculated. Using Ohm's law, the resistive voltage is calculated as 2 milliamps times 3 kiloohms equals 6 volts AC across the resistor.
Using Ohm's law to calculate the inductive voltage yields 2 milliamps times 9 kiloohms, or 18 volts AC.
Finally, using Ohm's law, the AC voltage across the capacitor is 2 milliamps times 5 kiloohms, or 10 volts AC. These resulting voltages can be represented in a phasor diagram. Note from the diagram that since the resistive voltage is in phase with the resistive current, the resistive voltage can be used as a reference for the capacitive voltage, which lags by 90 degrees, and the inductive voltage, which leads by 90 degrees. Also note from the same diagram that the inductive voltage is 180 degrees out of phase with the capacitive voltage.
From this information, let's confirm the total circuit voltage for this example RLC circuit.
Recall that the total circuit voltage, V sub T, is equal to the square root of V sub R squared plus the square of the quantity V sub L minus V sub C. Substituting the example values yields V sub T equals the square root of 6 squared plus the square of the quantity 18 minus 10. Completing the math yields the square root of 100, or 10 volts, for the total RLC voltage. Going back to the example, you'll recall that the applied voltage was 10 volts AC, which verifies the calculations, since the applied voltage and the total voltage are one and the same quantities.
Stop the program and complete activity number 2. When finished, continue watching the program.